Hello everyone. Today we are going to analyze this beam using stiffness matrix method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span BC and span CD. There is also an overhanging span AB. In the overhanging span, there is uniformly distributed load 12 kN per meter acting for the full span. In the span BC, there is a point load 48 kN. It is acting in the center of the span. In the span CD, there is a uniformly varying load. It varies from 0 in the point C to 90 in the point D. In the points B and C, there are hinged supports. In the point D, there is a fixed support. The overhanging span is 3 meter long. The span BC is 6 meter long. Span CD is 4 meter long. In this analysis, we have to find 5 moments. In the joints, there will be 2 moments. In the joint B, there are 2 moments, MBA and MBC. In the joint C also, there are 2 moments, MCB and MCD. In the fixed support, there will be a moment. In the point D, there is a fixed support. Here, we have the moment MDC. So, totally, we have to find 5 moments. Also, we have to calculate 3 reactions RB, RC and RD. In the joint B, we can easily calculate the moments because on the left of B, there is overhanging. To find MBA, we have to calculate the moment in the point B from the point A. In the overhanging span, there is a UDL 12 kN per meter. The length of overhanging is 3. Now let us calculate the moment in the point B due to the load 12 kN per meter. For that, we have to multiply this load with the distance and distance by 2. Here the distance is 3, so we are multiplying with 3 and 3 by 2. In this way, we are getting MBA, which is equal to 54 kN meter. The values of MBA and MBC will be same, but they will have the different signs. MBA is acting in the clockwise direction, so it will be positive. MBC is acting in the anti-clockwise direction, so it should be negative. But both of the values are same. To calculate MBC, we have to just change the sign of MBA. When we do that, we are getting minus 54 kN meter. Now let us calculate the fixed end moments. First, let us calculate the fixed end moments in the span BC. In the span BC, there is a point load 48 kN. It is acting on the center. The formulas to calculate the fixed end moments are minus WL upon 8 and positive WL upon 8. In the formulas, let us apply the values. W is 48, L is 6. After applying the values inside the formulas, we are getting M of BC and M of CB. Now let us calculate the fixed end moments in the span CD. In the span CD, there is uniformly varying load. It varies from 0 in the point C to 90 in the point D. The formulas for the fixed end moments are minus WL square upon 30 and WL square upon 20. Let us apply the values inside the formulas. W is 90, L is 4. After applying the values inside the formulas, we are getting m of CD and m of DC. In the stiffness matrix method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. In the roller support also, there will be slope. In this beam, in the points B and C, there are hinged supports. So the number of supports where slope occurs is equal to 2. In the point B, there is theta B, and in the point C, there is theta C. So in this analysis, there are two unknowns. If we calculate these two unknowns, we can easily find the final moments. Now let us make the fully restrained structure. In the fully restrained structure, there will be no slope. We know that only in the fixed support there will be no slope. So let us remove the hinged supports from the point B and from the point C and replace them with the fixed supports. In the fully restrained structure, no need to consider the overhanging span. Right now in this structure, there will be no displacement because all of the supports are fixed. That is why it is called the fully restrained structure. We have made the fully restrained structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates. The coordinates are in the point B and the point C because in these points only we have the unknown displacement, that is the slope. The coordinates should be made in the clockwise direction. You can see that both of the coordinates are in the clockwise direction. We know the formula to calculate the slope values. Delta matrix is equal to K matrix inverse into P matrix minus PL matrix. Inside the delta matrix, P matrix and PL matrix, we will have two values because in this analysis there are two coordinates. Inside the delta matrix, we will have the slope values theta B and theta C. In this formula, first let us calculate the PL matrix. We know that PL matrix is the moments developed in the coordinates due to the given load. In this analysis, there are two coordinates. In the point B and in the point C, we are having the coordinates. Inside the PL matrix, we have to apply the values very carefully. The first value should be from the first coordinate. The second value should be from the second coordinate. In the point B, we have calculated a fixed end moment m of BC. Let us apply that. In the point C, we have calculated two fixed end moments. We have to add both of them. After adding, we are getting minus 12. In this formula, now let us calculate the P matrix. The P matrix is the final forces or moments acting in the coordinate direction. The P matrix should be calculated in the order first from the first coordinate, then from the second coordinate. In the first coordinate B, we have calculated two final moments, MBA and MBC. Here we may have some confusion which movement we have to select. MBA is acting in the overhanging span, so we should not consider this. MBC is acting in the span BC, so we must select MBC. MBC is minus 54. Let us apply that. Now let us see the second coordinate. In the point C, we did not find any final movement because in the point C, there was no movement developed due to the overhanging. So for the second coordinate, we have to apply 0. In this formula, Now we are going to find the stiffness matrix. Now let us see how to calculate the stiffness values inside the stiffness matrix. For that we have to apply unit displacement in every coordinate. In this analysis there are two coordinates. They are in the point B and in the point C. So in these points we have to apply the unit displacement. Then we have to use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. Now let us see the size of the stiffness matrix. For 3 coordinates it will be 3 cross 3. For 2 coordinates it will be 2 cross 2. For 1 coordinate it will be 1 cross 1. In this analysis there are 2 coordinates. We already know for 2 coordinates the size will be 2 by 2. In this matrix, now let us find the first row. For that we have to apply unit displacement in the first coordinate. In the first coordinate B, there is a fixed support, but when we apply the unit displacement, it is no longer a fixed support, it becomes a hinged support. Because in the fixed support there will be no displacement. Now let us see how to draw this curve. We are applying unit displacement in the point B. In the point B, we have to make a clockwise curve towards the point C. Then we have to see the direction of the arrow. This arrow indicates downwards. So the curve comes below the span. We have to give some gap between the curve and the fixed support. You can see that I have given some gap between the fixed support and the curve because in the fixed support there will be no slope. That is why the curve ends before the point C and it cannot continue after the point C. Same like here, the ordinates should be made in the clockwise direction. Now let us calculate K11. For that, from the point B, we have to look on both the sides. On the left side there is nothing. On the right side there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of BC is 6. Let us apply that. Finally, for K11, we are getting 2EI upon 3. Now let us calculate K12. For that, from the point C, we have to look on both the sides. On the right side, there is no slope curve. If there is no curve, there will be no stiffness value. On the left side, there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of CB is 6. Let us apply that. Finally, for K12, we are getting EI upon 3 in the stiffness matrix. Now let us find the second row. For that, we have to apply unit displacement in the second coordinate. In the second coordinate C, there is a fixed support, but when we apply unit displacement, it is no longer a fixed support, it becomes a hinged support. Now let us see how to draw this curve. We are applying unit displacement in the point C. Point C is a joint. It is connecting the spans CB and CD. So we have to make two clockwise curves. One curve towards the point B and one curve towards the point D. Then we have to see the direction of the arrows. This arrow indicates upwards, so the curve comes above the span. This arrow indicates downwards, so the curve comes below the span. Now let us calculate the stiffness values. First, let us calculate K21. For that, from the point B, we have to look on both the sides. On the left side, there is nothing. On the right side, there is a hinged support. If the fair end is hinged, the formula is 2EI upon L. Length of BC is 6. Let us apply that. Finally, for K21, we are getting EI upon 3. Now let us calculate K22. For that, from the point C, we have to look on both the sides. First, let us look on the left side. On the left side, there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of CB is 6. Let us apply that. Now let us look on the right of C. On the right side also, there is a fixed support. So we have to apply the same formula 4EI upon L. Length of CD is equal to 4. Let us apply that. For K22, there are two values. We have to add both of them. After adding, we are getting 5EI upon 3. In the stiffness matrix, we have calculated both of the rows. Let us apply the values. EI is constant. Let us keep it outside. In this formula, we have calculated everything. Let us apply the values. EI inverse is equal to 1 upon EI. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and found the inverse. Then we have to multiply these two matrices. After multiplying, we are getting the values of theta b and theta c. In this analysis, we have calculated both of the unknowns. Now we can make the slope deflection equations and apply these unknowns and find the final moments. Now let us make the slope deflection equation for the span BC. In the span BC, only make the equation for MCB because we have already calculated MBC. So no need to make the equation for MBC and waste the time. Here let us apply the fixed end moment. Length of BC is 6 meter. Let us apply that. After applying the values of theta b and theta c, we are getting MCB, which is equal to 34 kilonewton meter. Now let us make the slope deflection equations in the span CD. In the equations, let us apply the fixed end moments. Length of CD is 4. Let us apply that. In the point D, there is a fixed support. In the fixed support, there will be no slope. So theta D will be 0. After applying the value of theta C in both of the equations, we are getting MCD and MDC. In this analysis, we have calculated all of the moments. Now we are going to find the vertical reactions. Let us take the overhanging span AB and the span BC together and calculate the vertical reactions. When we take them together, no need to consider MBA and MBC. They will get eliminated. We have to consider only one moment, that is MCB, which is acting in the clockwise direction. In these spans, first I am going to find RB. For that, I am going to take moment about C. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. This UDL 12 kN per meter is acting towards the point C in the anticlockwise direction. So it will be negative. The distance is 3. So minus 12 into 3. Then for the UDL, we have to find the centroid distance. Here the distance is 3. So the distance 3 by 2. We are taking moment about C. So we have to take this distance also. This distance is 6. So we have to add 6. RB is acting towards the point C in the clockwise direction. So it will be positive and the distance is 6. So 6 RB. The point load 48 kN is acting towards the point C in the anticlockwise direction. So it will be negative and the distance is 3. Then we have a moment. This moment is acting in the clockwise direction. So it will be positive. After the calculations, we are getting RB, which is equal to 63.33 kN. Now let us apply the rule sigma V is equal to 0. Using the rule, we can calculate RC1, which is equal to 20.67 kN. Now let us take the span CD and calculate the vertical reactions. In the span CD, there are two movements. MCD, which is acting in the anti-clockwise direction, and MDC, which is acting in the clockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. RC2 is acting towards the point D in the clockwise direction, so it will be positive and the distance is 4. So 4 RC2. This UVL is acting towards the point D in the anticlockwise direction, so it will be negative. For this UVL, we have to multiply the area with the centroid distance. We know the area formula of a triangle, half into breadth into height. Here the breadth is 4, height is 90. Using the values, we can calculate the area. Now we have to find the centroid distance. We are taking moment about D. In this case, we are moving towards the right hand side. For this triangle, the centroid distance towards the right is 1 upon 3 into breadth. Here the breadth is 4. So 1 upon 3 into 4. Then we have two movements. 34 moment is acting in the anti-clockwise direction, so it will be negative. 79 moment is acting in the clockwise direction, so it will be positive. Finally, we are getting RC2, which is equal to 48.75 kN. Now let us apply the rule sigma V is equal to 0. RC2 and RD are acting upwards, so both of them will be positive. The UVL is acting downwards, so it will be negative. To calculate the total load from this UVL, we have to find the area. We know the area formula, half into breadth into height. Using the formula, we are getting the total load 180. 180 minus RC2, we will get RD. Now let us add RC1 and RC2. After adding, we are getting RC. Now let us calculate the shear force values. I am going to start in the point A and move towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the shear force calculations. Using the shear force values, we can make the shear force diagram. Under the UVL, we have to make the shear force diagram in the shape of parabola. Now let us draw the free movement diagram. To draw this diagram, we have to consider every span as a separate simply supported beam. In the free movement diagram, no need to consider the overhanging span. In the span BC, there is a point load 48 kN. It is acting in the center. The formula to calculate the maximum bending moment is WL upon 4. Here W is 48, L is 6. When we apply the values inside the formula, we are getting 36. Using that, we can make this diagram. In the span CD, there is uniformly varying load. It varies from 0 in the point C and to 90 in the point D. The formula to calculate the maximum bending moment is WL square upon 9 root 3. In the formula, let us apply the values. W is 90, L is 4. When we apply the values inside the formula, we are getting 92.37 kilonewton meter. This maximum bending moment occurs at L upon root 3. Here L is 4, so it occurs at 2.31 meter from the point C. For the UVL, the bending moment diagram should be in the shape of parabola. Now, using the end moments, we can make the end moment diagram. Then we have to combine the end moment diagram and free moment diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.